Algebra 2, Chapter 17, Section 2, the standard deviation. So as we saw in 17.1, the mean, the median, the mode, and the range are not always a great summary of a sample. Another very useful statistic that we can use for summary is a statistic called the standard deviation. So the standard deviation, to define it, we first need to define a quantity called the variance. The variance of a sample is the mean of the squared deviations from the sample mean. So it's a mean of squared deviations from the mean of the sample. So that's a little confusing, and as we do examples, it'll make more sense. So we take the sum of the squared deviations and divide by the number of values that gives us our variance. The standard deviation is the square root of the variance, and often written with the lowercase Greek letter sigma, which you see here. So it's not a capital sigma like we've been doing with sigma notation. This is the lowercase sigma. So what this means is we take our x sub I, our data values in our set, or our sample, we subtract them from the mean. That's the x bar, and then we square the subtraction. So this result will always be positive because we square it. Add all those up to take the average of them, to add all those up, divide by n, and then take the square root of the result. So let's do some examples of this here. So let's find the standard deviation of the same sets that we used in 17.1a. So we have this set here. We already found the mean previously as 1.4 repeating forever, or 13/9. Okay, so to find standard deviation, we need to subtract each of these values from here to find the deviation. So start with our data values. We'll call them the x sub I. Okay, then we'll have subtracted from the mean and squared. Okay, and then we can sum them up at the end. Now we have several duplicate entries here, so we can calculate them once, but I'll keep track of all of them here so we don't lose track of how many we have of each. There's 3 zeros, 2 1s, 2 2s, a 3, and a 4. So getting our calculator out, we need to find the subtraction of these from the mean squared. So we have 0 minus 13/9 squared. Okay, we're just going to get an approximate answer here, 2.0864. And there's 3 of those, so we'll just write that down here. Then we have a 1, so we have 1 minus 13/9 squared is 0.19753. 0.1975. There's 2 of those, and 3. 2 minus 13/9 is 0.55 repeating forever squared is 0.30864. 0.30864. There's 2 of those. And then we have a 3. So 3 minus 13/9 squared is 2.419. So it's 2.4200. Because this it's 2.4198, sorry. Rounded wrong, 2.4198. And then 4 minus 13 over 9 squared, 6.5309. 6.5309. So you can see that these outliers, the things that lie towards the outside, that are furthest from the mean, contribute the most to this deviation. Okay? So now we're going to sum our deviations up. We don't need to sum the x sub i's because we did that when we found the mean. We just need to then divide by the number, which there were 9 of them. So our sum of our deviations is our variance. So our variance will be the sum of those things. So we have 2.0864, 3 of those, plus 0.19753, 2 of those, plus 0.30864, 2 of those, plus 2.4198, plus 6.5309 is 16.222. And if we then take the square root of that, that will give us the standard deviation, 4.0276 is our standard deviation. This standard deviation gives us a sense of how much spread there is in a data set. If the standard deviation is small, it means most of the numbers are close to the mean, and if it's very big, it means most of them are far away, or many of them are far away. So let's go on and look at B. So for B, we already knew that the mean, and by the way, another abbreviation you'll often see for mean is mu. We'll just use that here. This is the Greek letter mu. We saw the mean was 4.125 for B in 17.1. So if we write our x sub i's and our x sub I minus, this, I'll write mu this time. Well, let's just keep this x bar. But you saw the mu there, just in case you ever see that. That often means mean as well. So our squared deviations from the mean and our x sub I, we had 2.5, 3.4, 3.5, 7.1. So 2.5 minus 4.125 squared is 2.641. 3.4 minus 4.125 squared is 0.5256. 3.5 minus 4.125 squared is 0.3906. And 7.1 minus 4.125 squared is 8.851. So again, you see the biggest outlier, the one furthest from the mean, contributes the most individually. So we add these together, 2.641 plus 0.5256 plus 0.3906 is 12.407825. We take the square root to find the standard deviation, 3.5225. Part C, the mean of C was 1. So now we have our x sub I and our x sub I minus the mean squared, our individual deviations from the mean, squared deviations. So then we take minus 5 minus 1 and get minus 6 squared is 36. So here we have minus 5 is worth 36. And the 5s are going to be worth 5 minus 1 squared, 16. There's 3 of those. So adding all those together would be the same as 36 times 2 plus 16 times 3. Sorry, I realized it's off the screen there. And that gives us 120 for our sum, our variance. So our sigma will be the square root of that, 10.95. So we can see that while the mean is very small here, the deviation is big, meaning that this is a spread out data set. And then for D, this is a little silly because the mean is 7 and each of the entries is 7. So when we write our x sub i's and our x sub I minus the mean squared, each of these deviations from the mean is going to be 0 because 7 minus 7 is 0, squared is 0. And the sum is 0, so the variance is 0, and the okay, so I realized after doing all that work that I made a big mistake. Hopefully you caught it while you were watching the video. So if we go back and look at the definition of variance, we're supposed to divide the sum of the square deviations by the number of values, which I've forgotten each step. Okay, so if we go back to A, let's fix this. This is incorrect, and this is incorrect. The variance is supposed to be the sum of the deviations divided by the number of entries. So we still have our sum here, so we can fix our work without too much redo. So 16.22 should have been divided by 9 to get the variance. 1.802 is the actual variance. And then we take the square root. So sorry for the confusion. 1.342 is the standard deviation for A. So here you see the standard deviation is close to the value of the mean, but it doesn't mean much. It just means that our spread is kind of small compared to some of the data sets we'll see in a minute. So for 2, we have the wrong answer again because the variance is the sum of the deviations divided by the number of things, which there's 4 things. So we should have had 2.641 plus 5.5256 plus 0.3906 plus 8.851 divided by 4, 3.10205. That should have been the variance, and the square root of that, 1.7613. So 1.761 is the standard deviation for B. So you can see that the standard deviation for B is bigger than A because there's more variance from the mean. The dividing by n gives us the correct weighting for our statistic, so not doing that was a big mistake. And then for part C, again, the variance should have been 120 over 5, the number of entries in our sample. And then the square root of that would be the standard deviation. 4.899. You can see here the standard deviation is very big. It's almost as much as the spread here between these numbers and the mean. And that's because they're so spread out. There's not very many things close to the mean. And then for 7, the variance would be 0 over 3, which is 0. And the standard deviation is the square root of 0, which is 0. So that one has a 0 standard deviation because there is no deviation. All the numbers are the mean. So hopefully, after fixing that mistake, now this makes a little more sense and you can understand better how to find the standard deviation.